Right, hello. This is a series of videos that we are putting together to help students to understand the big picture of chemistry. There are a series of 6 videos. If you are a foundation student, you need to watch the first 4, and if you are higher, then you watch all 6. They've been put together to try and link all the ideas of the different subjects in chemistry so that you can see how they all fit together. Now, you're taught in Year 9 all the topics for Paper 1 and in Year 10 all the topics for Paper 2. But this is just an idea of putting them all together. Now, if we look at what you actually sort of need to know about chemistry, there's certain areas. So you've got the periodic table, bonding, something we call NACHO chemistry, the required practicals, calculating moles, and Le Chatelier's principle. And today we're just going to concentrate on the periodic table. So let's just have a look then. We need to know about the structure of the periodic table and how it came about, and also our understanding of atoms and their development. So first of all, if we have a look at the periodic table, you need to understand why it's set out the way it is. And once you understand that, actually it makes a lot of sense. And I actually think it's a really clever piece of work, even though when you look at it to start with, you think to yourself, the table hasn't got a proper sort of shape. It actually does make sense. So if you look, first of all, you've got group numbers going down. So this is group 1, group 2, and over here you've got 3, 4, 5, 6, 7, and then group 8, or also known as group 0. That group number means that everything in that particular column of that group has got that number of electrons in its outer shell. So, for instance, if the chemical's in group 4, it's got 4 electrons in its outer shell. If it's in group 1, it's got 1 electron in its outer shell. There is a section in the middle here called the transition metals that don't quite fit that pattern. But they're there because all of the chemicals, if you look carefully, all run in atomic number. So if you have a look then, the other thing you need to know is about the periods. If we look at the rows, we've got row 1 at the top, and that's got hydrogen and helium in it, and that's period 1, period 2, period 3, and so on. Now those actually mean something as well. So the period number is the number of shells that that particular atom has got. So if I look at lithium, for instance, I can say lithium is in period 2 and it's in group 1. So that tells me it's got 2 shells because it's in period 2 and it's got 1 in its outer shell. So if I work backwards, the inner shell is always full up with 2. So the electron structure for lithium will be 2, 1. If I looked at the next one down, sodium has got 3 shells and it's in group 1. So that means if it's got 3 shells, there's 2 in the first shell, 8 in the second shell to fill it up, and then when we go into the third one, because it's in group 1, it's only got 1 electron. And then the same for potassium, it's got 4 shells, so it's 2, 8, 8, 1, and so on. This here in the middle is the key. This is on your periodic table you will get for your exams, and lots of people don't look at it, but it actually tells you what the numbers mean. The bottom number is the atomic or proton number, and the top number is the mass, and that's the mass in the nucleus of the neutrons and protons added together. If you take the proton number away from the mass number, you will work out the number of neutrons. Now, there's another little thing here, which I like to call the stairway to Devon. Now, originally, I just thought about that as looking like a set of stairs. And then I thought about the song Stairway to Heaven. And then I actually thought, well, we're in Devon, so we'll call it the Stairway to Devon. And that is actually really important because everything on the left-hand side of the stairs is a metal, and everything on the right-hand side of the stairs is a non-metal. And the reason that's important is because you need to know that for bonding, because if you've just got metals reacting, that's metallic bonding. If I've got a metal and a non-metal, that's ionic bonding, and if I've just got non-metals, that's covalent bonding, and you'll see that in the next video. So So let's have a little look at the different groups and their properties. You may be asked to talk about some of these. So let's start with group 1. Group 1 are called the alkali metals because if I put the group 1 metal into water, it will start off being green with universal indicator because it's neutral, but when you put the metal in, it will turn the water purple because the metal has made the solution an alkali. Group 1 have 1 electron in their outer shell. They are more reactive the further down the group you go. They are stored in oil to act as a barrier so that oxygen or air or water do not react with group 1 because they are really, really reactive. However, group 1 also loves group 7 because if you think about it, a full outer shell has got 8 electrons as long as it's not the first shell. And so group 1 and group 7 love to get together to make a full outer shell, and that would be an ionic bond. We also have group 2 and group 6, or you could have 2 group 1s and 1 group 6. Okay, so if we have a look at group 2 then, group 2 are called the alkali earth metals, and they have 2 electrons in their outer shell. The thing we talk about with group 2 is that most times they talk about group 2 being attached to a carbonate. A carbonate is a chemical that can be broken down by thermal decomposition to make carbon dioxide. So if you ever see CO3 or anything that's a carbonate, you just think straight away that makes carbon dioxide. And to test for a carbon dioxide, you bubble the gas through lime water and it will turn cloudy. The transition metals in the middle. They sound posh, but essentially they're just metals. And if you think about what do metals actually do, what are their properties, they conduct electricity and heat, they're used as catalysts, they're hard and shiny, they're ductile and they're malleable. Any one of those would do as properties. Group 7 are known as the halogens. They are non-metals and they are more reactive the further up the group you go. So fluorine at the top is the most reactive. Now the reason that chemicals are reactive in group 1 going down and group 7 going up is because in group 1 they've just got 1 electron in their outer shell and they are desperately trying to hold on to it. And the electron has got a negative charge and the protons have got positive charge and they're trying to hold on. So if I've got 11 protons and I've got 11 electrons, those protons are trying to hold on through 2 shells of 2 and 8 and then trying to hold on to that 1 in the outer shell. And the further away that 1 gets, the harder it is to hold on. Whereas with group 7, it's the opposite because they've already got 7, so it's much easier to attract an electron. And this is what we call shielding, where the shells are in the way of trying to hold on to the charges. Group 7 are more reactive the further we go up, as I said, but also they travel in pairs. You will never find a group 7 chemical on its own, and we call that diatomic. Just like carbon dioxide is 2 oxygens. And like I said, they love group 1. You can also have group 7 chlorine, which will attach to calcium, so you can get calcium chloride. But calcium's in group 2, so that means I need 2 group 7s to take 1 each of the electrons. And then we've got group 0 or group 8, and they're the noble gases. They've got a full outer shell. They generally don't react with anything, and we call those gases. Okay, so let's have a look at the development of our knowledge of the atom and the periodic table invention. So, first of all, in Greek times, about 2,500 years ago, there was a chap called Democritus. And he said that everything was made of atoms, and he called it atomos. But nobody believed him at the time because there was this other famous scientist called Aristotle who said that everything was made of water, wind, earth and fire. And because he was such a great, renowned scientist and philosopher, Everyone believed him, and it was for about 2,000 years that actual theory stood, until we had Dalton, who actually said, actually, I think everything is made of atoms. And then we had the real developments taking place. But if you look at the year, we're not talking until 1897. And this is where J.J. Thomson came up with the plum pudding model. And he said that the atom is a ball of positive charge with electrons embedded in it. And this is what he thought atoms looked like. So they'd got the negatives in with the positives. Well, Rutherford and his two assistants, Geiger and Marsden, said, actually, if that's the case, if everything is made of a plum pudding, then if I take some gold foil and I fire some alpha particles into it, then they should just go straight through. It worked out that actually some of them deflected. And they said, well, if they deflected, then there must be something on the outside. So there must be some kind of other charge, which they called electrons, on the outside of the nucleus. And that's where the nuclear model came in. And that's their experiment that they carried out. Then we've got two other scientists that discovered two more parts of the atom. So Niels Bohr, and I always say boring Bohr, because he said that actually the electrons just orbit round the nucleus. And if you think about electrons orbiting around and around and around and around, I think that's quite boring. So that's Niels Bohr saying that. Whereas James Chadwick discovered neutrons. And I always try to remember this by saying that Mr. Chadwick, who is in charge of behaviour at our school, he is not allowed to be positive or negative because he's in charge of behaviour, so we say he's neutral. So the neutrons, Mr. Chadwick is discovered neutrons. Then if we look at the actual periodic table and how that came about, first of all in 1864 there was a scientist called Newlands, and at that time we only knew about 63 chemicals. And he tried to put them into some kind of logical order, but the problem was he didn't realise that we hadn't discovered them all, and he got really stuck. And it was only when Mendeleev came along and he said, actually, if you leave gaps in the periodic table for the ones that we don't think we've discovered, then actually that would be much better, because it shows the atomic number, the atomic mass, and then running in order. And this created a real excitement in the scientific world, because then scientists were going all around the world trying to find the chemicals that actually went into the gaps. And I think that's actually quite crucial. Okay, so that's the first video of the series to do with the periodic table structure. One last thing I will say is, if you look at this periodic table at GCSE level, you don't need to know these chemicals all at the bottom here. You will not be asked about these generally in any GCSE question. They generally ask about group 1, group 2, the transition metals across there. They might ask a little bit about the groups here. Group 7 and group 0 are the main ones that you get asked.